Hello, bachcho, welcome. So, today we are going to learn a very important topic from our unit on electrostatic potential and capacitance. We'll be talking all about capacitors. Now, इसमें टेंशन लेने की कोई बात नहीं है, I promise. We will make this concept so simple that you'll remember it for life, and it'll be completely safe for your exams. Chalo, let's dive into this.
So, have you ever really thought about this? I mean, how can a tiny battery inside a camera produce a flash that's so incredibly bright? The battery itself isn't that powerful. Well, it has a little helper inside, something that stores up energy slowly and then releases it all in one powerful, instant burst. That helper, my friends, is a capacitor. And today, we are going to understand exactly how it works.
Okay, so to get this idea, let's forget about all the complicated physics for just a minute. We're going to use a really simple analogy, something you see every day. A water bucket.
That's it. Just imagine a capacitor is nothing more than a bucket. But instead of holding water, this special bucket holds electric charge. Just keep this picture of a bucket in your head. Trust me, it's going to make everything super clear.
Look at how nicely this fits. The water we're pouring into the bucket, well, that's just like the electric charge, which we call Q. And the water level, the pressure it creates at the bottom, that's our electric potential, or V. But here's the most important part, the width of the bucket itself, its ability to hold water. That is its capacitance, C. See, it's a perfect match.
Just think about it, right? If you take a really wide bucket and a very narrow one, and you pour the exact same amount of water in both, which one will have a lower water level? The wide one, obviously. It can hold more water before the level gets high. It has a higher capacity. A capacitor works in exactly the same way.
Okay, so the bucket analogy gives us a great mental picture. But for the exam, you need the official stuff. So let's look at the proper NCERT definition that will get you full marks.
So the textbook says it's the ratio of charge to the potential difference. Now don't let the big words scare you. All this is really asking is, for a given amount of electric pressure, or V, how much charge, Q, can this thing store? That's all capacitance is. It's the storing ability.
And this gives us our key formula. C equals Q divided by V. It's just a mathematical way of saying what our bucket analogy showed us. Capacitance is just how many coulombs of charge you can pack in for every 1 volt of electric pressure you apply. And we measure it in a unit called the farad, named after the great Michael Farad.
Right, let's move on and see how this whole concept is built, step by step. Physics isn't about just memorizing formulas. It's about understanding the story behind them. So let's see the story of Q, V, and C.
It's a very logical flow. Step 1, we start putting some charge onto a conductor. Simple. Step 2, as we add more and more charge, the electrical pressure, the potential, starts to rise. Just like pouring more water makes the water level go up. Step 3, now what we observe experimentally is that the charge Q is directly proportional to the potential V. Double the charge, you double the potential. And step 4, whenever we have a proportionality in physics, we introduce a constant to make it an equation. And that constant of proportionality here is our capacitance, C. And that's how we get the most fundamental equation, Q equals C times V. Let's try a very small problem to make this concrete. Imagine you have a 10-volt battery, and your job is to build a device that can store 20 coulombs of charge using this battery. What capacitance will your device need to have? Well, we just use our many formula. We need to find C, and we know C equals Q divided by V. So we just plug in the numbers. That's 20 coulombs divided by 10 volts. And what we get is 2 farads. Now, just so you know, 2 farads is actually a huge capacitance. In real electronics, we usually work with microfarads or even nanofarads. This just shows you that 20 coulombs is a massive amount of charge.
Okay, now for a very important point. Bachchum, please note this down because this is a classic silent killer in exams. It's a mistake so many students make, and it can cost you easy marks.
So the trap is right there in the formula. C equals Q by V. A lot of students look at this and think, V is in the denominator, so if I increase the voltage, the capacitance must decrease. No, this is completely wrong. The correct idea is that capacitance, C, is a fixed property of a capacitor. It only depends on its physical construction, its shape, its size, things like that. If you increase the voltage, the capacitor simply stores more charge to keep up. The ratio of Q to V, which is C, stays constant.
Let's go back to our bucket analogy one last time. Does the size of your bucket change just because you pour more water into it? Of course not. The bucket's capacity is fixed. It is what it is. A capacitor is just the same. Its capacitance is a fundamental fixed property. So please, don't fall into this trap. So, let's wrap this up. We'll quickly connect this idea to the rest of the unit and then summarize the most important points for your notes. This will be great for a quick revision just before your exam.
Now, why did we spend so much time on this one idea? Because understanding what capacitance is, and more importantly, what it depends on, is the absolute foundation for our next big topic, the parallel plate capacitor. We're going to use exactly this idea that capacitance depends on geometry to derive one of the most important formulas in this entire chapter.
All right, here are your key takeaways. Write these down. Number 1, a capacitor is a device to store electric charge and energy. Number 2, the main formula is Q equals CV. Number 3, capacitance is measured in farads. Number 4, and this is the big one, C depends only on the geometry, the shape, size, and spacing. And number 5, which follows from that, C does not change when you change Q or V. Remember these 5 points and you are all set.
And I'll leave you with a final question to think about. We know that a capacitor stores energy, right? Like a stretched spring. But where is this energy actually located? Is it stored in the metal plates that are holding the charge? Or could it be stored in the empty space, in the electric field between the plates? Ponder that for a bit. We'll discover the answer together in our next session. Keep learning.